In the mountainous heart of Japan, thousands of feet beneath the southern Alps, a pathway is being carved.
This is not just another tunnel. It is the route for a train that will move not on wheels, but by floating on magnetic force.
The project is called the Chuo Shinkansen, Japan's superconducting maglev line.
Its first phase alone is expected to cost around $72 billion for a single route. This railway is more than an engineering project. It is a test of Japan's technological ambition, political will, and economic future.
The dream of magnetic flight began decades ago, soon after Japan changed the world with the original Shinkansen.
When the Tokaido Shinkansen opened in 1964, it proved that Japan could lead the world in rail technology.
But even while that first bullet train became a national symbol, engineers were already imagining something faster.
Their idea was radical. Eliminate the friction between wheel and rail completely.
Instead of rolling on steel, the train would float above the guideway and surge forward using magnetic force.
It sounded like science fiction, but the physics were real. The challenge was turning theory into a transportation system.
For decades, Japan poured resources into research, test tracks, and experimental vehicles.
In 1997, the Yamanashi Maglev test line opened north of Mount Fuji to prove the future was possible.
There, year after year, Japan pushed the boundaries of speed in the mountains. In 2015, that test line made history with a world record speed of 603 kilometers per hour.
That is 374 miles per hour, faster than any conventional train has ever traveled.
But setting records is one thing. Building a commercial railway for millions of passengers is another. At the heart of the system is a technology that feels almost unreal: superconducting magnets. These magnets are cooled to nearly absolute zero, allowing them to generate extraordinarily powerful magnetic fields.
Mounted on the train, they interact with coils built into the guideway walls.
At first, the train moves on rubber tires like a normal vehicle.
Then, at around 100 miles per hour, something remarkable happens. The train begins to rise.
The magnetic forces lift the train about 10 centimeters above the track, removing physical contact entirely.
There are no steel wheels grinding on rails, no traditional friction, and almost no mechanical contact at all.
That makes the ride incredibly smooth and opens the door to speeds conventional rail can never reach.
But this miracle of motion comes with serious trade-offs.
Keeping superconducting magnets cold requires constant cryogenic cooling and enormous energy. At 500 kilometers per hour, air itself becomes a major enemy.
And because this route runs mostly through tunnels, that air resistance becomes even more severe. Engineers call it the piston effect, pressure building in front of the train as it races through a confined tube.
That means the maglev uses significantly more energy than Japan's current bullet trains.
Even so, Japan believes the speed advantage changes everything.
A trip from Tokyo to Nagoya that now takes 90 minutes could be cut to just 40.
The scale of the Chuo Shinkansen is almost hard to comprehend.
The first phase will connect Shinagawa in Tokyo to Nagoya across 286 kilometers.
Later, the line is planned to continue all the way to Osaka.
Nearly 90% of the route will run inside tunnels. Stations in Tokyo, Nagoya, and Osaka will be built deep underground, to avoid disrupting the cities above.
Between those cities, the route takes the most direct path possible, straight through the Japanese Alps.
That is where this project becomes truly astonishing.
The Southern Alps Tunnel will stretch for about 25 kilometers through some of Japan's most rugged terrain.
At its deepest point, it will sit around 1,400 meters below the surface. That is deeper than many of the tallest buildings on Earth are high.
Slow the rotation. We've got high pressure reading on the north wall. Get the shotcrete team ready.
At those depths, the mountain pushes back with crushing pressure, unstable rock, and unpredictable groundwater.
The shear stress readings here are higher than the model creek.
Yes, but the core sample confirms the presence of stable mineralization at this.
They also use advanced boring technology that can probe up to 1,000 meters ahead of the tunnel face.
Look out, she's gonna blow! Fire!
Get back, move! Mayday, we have a breach at the face.
In 2026, several sections were delayed after engineers discovered rock far more fragile than expected.
It was a brutal reminder that geology does not follow project schedules.
And every delay pushes the cost even higher.
When approved in 2014, the Tokyo to Nagoya section was expected to cost about $36 billion.
By 2021, that estimate had surged dramatically.
Now, with delays and new challenges, the total has moved toward $72 billion. That makes it one of the most expensive infrastructure projects ever attempted by a single company.
The tunnels account for the largest share of that price.
Then come the underground stations, earthquake protection systems, and the extraordinary trains themselves.
But the most difficult obstacle was not underground rock. It was politics.
In Shizuoka Prefecture, just 9 kilometers of route nearly derailed the entire project.
The problem centered on the Oi River, a vital water source for farms and tea fields downstream.
Shizuoka worried that tunnel construction beneath the watershed might alter underground water flow.
If the river lost water, agriculture across the region could suffer.
Mistress. As you can see, the drainage system utilizes a multi-stage filtration process before the water is reintroduced.
And we cannot back down on the central line. It is critical infrastructure.
Go home! We do not want this!
Without permission from Shizuoka, the Southern Alps Tunnel could not move forward. The delay shattered the original 2027 opening target.
For years, the standoff became a national debate over environmental risk and strategic infrastructure.
Then, in 2024, the political situation changed.
A new governor, Yasutomo Suzuki, was seen as more open to compromise.
JR Central agreed to compensate for water resource impacts, even without requiring proof that the project caused them.
That allowed preliminary work in Shizuoka to begin at last.
But the lost years could not be recovered. The opening date moved further into the 2030s.
So why keep going? Why build this line at all?
One answer is capacity. The existing Tokaido Shinkansen is already one of the busiest rail lines on Earth.
Japan needs another route between Tokyo and Osaka to keep its economic core moving.
Another answer is resilience. The coastal Tokaido route lies near the predicted zone of the Nankai Trough megaquake. The Chuo Shinkansen takes an inland path through the mountains, creating a crucial backup if disaster strikes.
In that sense, this train is not just transportation. It is strategic national insurance. There is also pride at stake. By commercializing superconducting maglev, Japan could lead the world again.
Improvers. If successful, the Chuo Shinkansen could become a model for future export projects overseas.
Mountains do not care about deadlines, budgets, or political promises.
Yet meter by meter, the tunnels continue to advance beneath the Alps.
If the line opens in the 2030s, passengers may one day travel from Tokyo to Nagoya in just 40 minutes.
What looks today like an expensive gamble may someday be seen as another defining moment in Japan's engineering history.
Until that day arrives, deep beneath the mountains, Japan's train that flies through rock